Okay, welcome back. We're going to be doing another video on the nerve block modeling repository, and today we're specifically going to be looking at our threshold detector. We're going to dive into some of the code that's behind this because there's a lot of things going on, and making sure that you're comfortable knowing the whole process of how we find the block threshold, minimum amplitude required to block. So obviously we're not blocking right here. And we're going to go through the code behind it, but first we need to understand the process. So we can look at the overall algorithm, and then from there we can look at the implementation. So essentially we're going to set some bounds for where we know it's the minimum amplitude and the maximum amplitude, and somewhere in between is the blocking amplitude. So first we pick an amplitude in that bounds. We're going to do a binary search. So we're going to pick the one in the middle, and then from there we can figure out where to go. So we set the electrode amplitude. From there, these two diamonds here, these two conditionals, are actually going to be two whole runs of a simulation. The first run, all we're going to do is run the blocking stimulus with nothing else, and we're going to see if that causes continuous activation, or if it causes activation sufficient enough that it's going to go all the way till our test action potential. So if we know that we're not going to be able to fire a test action potential because there's still a bunch of activation from our blocking threshold, then we already know that this isn't going to work for blocking. And from there we can pick higher amplitudes. We know we have to increase the amplitude before we can reach a steady state. Okay, so let's say instead of continuous firing, we reached a steady state. From there, what we can do is we can test whether it'll block an action potential, and that's where it either blocks or it fails to block. And so we're going to do this. We're gonna pick an amplitude. We're going to divide our bounds. We're going to add the two, divide them by 2, and then we're going to have, the average right in the middle. And we're going to take that amplitude and test it. And sometimes we might only need to run one run. Sometimes we might need to run 2. And then from there we know whether, since we divided our search space in half, we have the upper half and the lower half. When we choose a higher amplitude, we know that somewhere in that higher range is our block threshold. So this is kind of the overview. We'll come back to this as we start reading through the code, and you can see how this lines up with the code. But so I went to the nerve block modeling repository, to the current simulation folder, and in there's a file called threshfinder.hoc, and that is the file that contains the entirety of our block threshold finder, the threshold detector. So let's start reading through this and let's see what we can figure out. So first off, obviously, if we're going to be figuring out whether we can block, we're going to need to be creating test action potentials. And that is what the stim clamp is for. It's set at the 0th node. The 0th node being, if you're orienting yourself based on this graph here, it's the very first node of the graph, which obviously in computer science is going to be node 0. So we're going to need to be setting the parameters for that electrode a lot, and instead of typing them all out every time, we have a nice set stim method which will set the parameters. It should be noted that when you start up the nerve block repository, when you just start up and you load the cnow run file, the set stim is going to be set, which means if you want to start running other things and not have the test action potential, you're going to need to turn it off. And you can just do that by using the set stim and just doing 3 zeros as the parameters or the arguments. So that's our test stimulus. The other function up here they're kind of just two really useful functions. this one is going to set the amplitude of the blocking electrode. Now, this can have a lot of things to it because we don't necessarily inherently know which electrode we're using. We're going to have to figure that out. And that's what all this logic is here for. It figures out which electrode is being used and how many of them are being used. So that's kind of the point of this whole chunk of code here. So, we have the sine waves. So we have the sine electrode. We have square waves, balanced and unbalanced. We have triangle waves. We have the DC sine. And then we have the set amplitude electrodes, which I believe goes to the electrode API. From there, we can count initial spikes. So this function, we kind of set ourselves up here by being able to set amplitudes of our test pulse and of our blocking electrode. We made that pretty modular, so we don't have to worry about that now. So from here, we can just start thinking about our algorithm of how we're going to go through this. So the function of count initial spikes is essentially what we're using to do the continuous firing test. We're checking, how many spikes are there going to be, or is it continuous firing? So we reset our AP counters, our action potential counters. We're going to reset them, and we're going to turn off our stim because we don't want to test the test pulse yet. We just want to look at our blocking electrode. And so we're going to use this, has two parameters passed to it. The first one being the amplitude and the coefficient of relating to anodic and cathodic charge. And that's only necessary for round balanced waves. So usually you can just pass it to 0 and not worry about it. So we set the amplitude of our electrode. And from there, we can run the simulation. So now all that's running is just the blocking electrode, and we can return the number of action potentials that were counted. So that's the first, diamond here, our first conditional block where we're doing one test. So the next chunk of code is kind of, it takes this into account, but it's also, because we modularize this out to another function, we don't have to worry about it too much in this next chunk of code. We can just call that when we need to. The test waveform, it's going to do a bunch of things. So first, we're going to check the number of action potentials, which is obviously the step. So we're just going to call our previous code. There are a couple of stipulations to that. If we're running in efficient mode, which means we know for a fact that this isn't going to cause continuous activation, and we actually know exactly how many action potentials are going to be generated, we can use efficient mode to skip that first run entirely, which technically would cut down our runtime by a factor of 2. So that's it. But the condition for that is that you have to know exactly how many action potentials are going to be created. But if you don't know, then we're going to run it, and we're going to then check if we reached a steady state. And if we didn't, we can just end right there. We can end right there, return -1, and that defines our never reaching a steady state. So after we've run it, we check we reach a steady state, we're going to reset our AP count objects so that we don't keep counting. We want to go back to 0 so we can count again for the next run. So we're going to set the stimulus, and we're going to set the blocking electrode, and run another simulation. And so these two steps here are the second diamond here, where we're checking if we can block a test pulse. And from there, we can return a value of whether or not we successfully blocked or we failed to block. And we're going to give output to the console at the end. So the other thing to note is we have a stop flag that's at the ready, so when anybody ever clicks the stop button, everything stops and it doesn't keep running. Because traditionally, if you just had the stop button hooked up the same way as this stop button up here on the run control, this stops the simulation, but all that tells neuron is that if we scroll down a little bit, there should be a run command that runs a simulation. And this command is over when the simulation stops. And so all that happens if we just stop it is we've just finished this command, and then we continue iterating through our process, which is not what we wanted. So we set up the stop flag to cut all code from continuing to execute. So let's look at some of these parameters. Obviously, we have all the parameters for the test pulse. We also have the 2 parameters for the blocking waveform. So at the beginning, we can check if the stop flag and immediately leave. That's pretty easy. From here, we need to do our first step, which is checking if we're reaching a steady state. So we have the, first off, we're going to, assuming we're not in the efficient state. If we're in the efficient state, we already know the number of spikes, the number of action potentials, and we can just save that and move on. But if you're doing normal runs, we're going to need to run that count initial spikes method from above with our 2 parameters. And from there, when it's done, what we can do is we can check whether or not it's going to interfere with our test pulse. So we can get the time of when the action potential arrived, the very last one. We can check it against when our test pulse is going to be generated. So we're looking at the last action potential generated from the blocking electrode compared to the test pulse that we're going to fire. And if the gap between them isn't at least 5 milliseconds, that being the blocking electrode is finished its set of action potentials at least 5 milliseconds before we are going to send our test pulse. If it doesn't meet that qualification, we're going to know that this isn't reaching a steady state in time and return -1. We're also going to print the output no steady state. From there, we have the efficient state, and we're going to check the stop flag again. So we ran it once. That was our first run to check the number of action potentials and reaching a steady state. We're going to run it a second time now. We're going to set it, but this time we're going to have the test pulse at the ready, and then we're going to run it. From here, now we've just run our simulation, the second one, that is the test pulse blocked. And from there we can tell whether it was blocked, whether it wasn't blocked, and we can return that. We can print it and return it. So those are the 2 methods that make up one iteration of this this flowchart. But then we're going to set a higher amplitude or a lower amplitude and repeat. That's the key right there. That's part of the binary search. Is you cut the search space in half, and then you reiterate, and then cut the half into a fourth and continue until we reach some value. So that is what the find threshold function is for. So we're going to have a whole bunch of parameters. First, we have the upper and lower bounds of our search, and we're going to look at the threshold for an action potential. So that's the minimum voltage across a node, specifically the last node where we're measuring the action potential, whether it's reached there or not. This is the voltage value that's going to trigger whether or not we've reached an action potential. So I think normally it's either 0 millivolts or -10 millivolts or something around there. From there we have our 3 stimulus parameters for the test pulse. The wave coefficient you don't really have to worry about, but the resolution is the resolution of the search. So what's the minimum amount of range that we're going to deem is good enough? Okay, we're going to check for valid parameters. Obviously, we can't have the one, they can't be flipped. Our lower value has to be less than upper value, and if it's not, then that's an invalid range. First off, we have to make sure the action potential controller is connected. So this is we have two action potential counters, one on one side, one on the other side of the axon. And we need to make sure they're connected and set their thresholds so everything's set up. So now these are set up and ready. And from here we make sure our stop flag is good. The set flags, this is kind of important. We need to do something throughout this algorithm. We need to make sure that we have blocked at least once, we have passed an action potential at least once, and we've reached a steady state at least once. Which means if all we ever did was never reach a steady state, then we haven't found the block threshold. If all we ever did was block action potentials, then we also know we never reached the block threshold. And if all we ever did was not block action potentials, we never reached the block threshold. These two being we never did high enough to block, whereas this, when we successfully block, we've never reached a state where we know for a fact that this is the lowest amplitude for block. And that's the block threshold, is the lowest amplitude required to block. So we initialize our level, which is essentially going to be our test amplitude. We're going to print out the header for the output, and we're going to start our algorithm. Now, the first thing to note is this algorithm is really 2, because we have to flip it for positive and binary searches, so positive and negative searches. We have to flip the whole algorithm a little bit. So that's why that's there. From there, we can check whether or not we've sufficiently reached our resolution or if the stop flag. And if we haven't yet, we're going to keep iterating through. We pick a level that's the midpoint of the two amplitudes. That's the binary search part of the binary search algorithm that we're doing. We're going to test the waveform, which is the entire process of this. So it's one whole iteration of both runs. And then that'll tell us whether or not we've 1 been blocked, 0 is not blocked, -1 is never reached the sufficient state, so never reached a steady state, and -2 is it was stopped. The stop flag was set. So depending on that, we can tell whether it was blocked, and if it was blocked, we know that we need to go to a lower amplitude. So we need to search below the current level. So we set up the upper value to our level, which takes the bottom half of our search space. And on the flip side, we're going to take the top half of our search space if we didn't block. From there, we can set flags on whether or not we've reached the steady state. So this is the checks to make sure that we have blocked and passed action potentials. And then we have the flip of that. So same thing, but with the negative value, and you can figure that out for yourself. Hopefully, that's pretty easy to see how things flip. From there, we need to check those parameters to make sure we've blocked. And if we haven't, we haven't blocked, we know the range was insufficient. So if we haven't blocked, we know the range was insufficient for blocking. If we haven't passed an action potential, the range was insufficient for allowing action potentials. If we haven't reached a steady state, etc. And then we can check if any of them occurred, we can return a 0, as opposed to returning our block threshold. So if we had a successful search at this point, which means we passed all 3 of these, print and return the minimum value for blocking. So the threshold for block is whichever of these. It depends on whether you did the positive block or a negative block. And so that's the whole thing. That's the binary search, which essentially runs an iteration of this flowchart. And then we have our output methods that just make things look pretty in a comma separated formats, you can easily put them into any analysis program that you're running. The last things to note are we also have the entire GUI is at the bottom of this file, and the initial parameters are set. So the set initial parameters are here. This calls the set stim. So I'm assuming at the bottom of this file we have the set initial parameters, which means the set stim is called. And then we have the stuff for drawing it. If you're used to Neuron, you're probably used to all these panels and button values and stuff. And the key thing to see here, the X button for find threshold, this is our whole command for running our block threshold algorithm. We have a lower bound and upper bound, the action potential threshold, the minimum the minimum voltage that we're going to count as an action potential, and then the stimulus parameters for our test action potential, and the anodic coefficient, and then the resolution of our search. And then from there, we're going to just draw we're going to set the initial parameters, we're going to draw the two, and we also have a stop run function that makes sure that when somebody stops the run, we stop everything. So last thing to look at is to look at maybe some output from the algorithm, and I made sure that when we output stuff that we output what it is. So we output the test amplitudes. You'll notice this kind of goes like up and down a little bit, and that's the binary search where we're going back and forth honing in on the block threshold. Was a stable state reached? So that was the first thing, and you'll notice that, so that's the second column. For all of these, a stable state was reached, so that's good. The count proximal spikes with stimulus, so that's on the left. So that is the number of action potentials that are seen on the left side when you include the test action potential. And the two columns later is the number on the right. So, well, we can see the last value being whether it was blocked. On the lines or tests where it was blocked, you can see between column 3 and column 5, when it was blocked, there is one less action potential seen. So on the left side, we saw 5 action potentials, but on the right side, we only ever saw 4, and that's because we blocked one of the action potentials. And then the last column is just going to be number of action potentials. Well, the second to last one is the number of action potentials seen when you didn't use the test pulse. So how many action potentials were there when you just turned it on with no test pulse? And usually you can see how we always had one more than the other one. Sometimes when you fire a test pulse to the blocking electrode, sometimes it might send multiple action potentials out, and then you'd be able to see this from here. But in the end, all we really need, at least for our purposes right now, is the last line where we say our threshold for block was, and then we print it out. So that was a detailed view at the block threshold finder and the algorithm behind it. And we'll see you in the next video.